Welkom terug op het tweede deel van het webinar met de presentatie rond de dynamische modelleerstudie diepe ondergrond. De sprekers in het bureau worden straks voorgesteld. Maar misschien even nog de praktische afspraken herhalen. Dus zoals jullie zien wordt er een opname gemaakt. Graag jullie camera's en micro's uit. En de vragen kunt u stellen via de chat en die zullen achteraf overlopen worden. De slides en de opname zullen ook achteraf bezorgd worden aan iedereen die is ingeschreven. En nu gaat Helga een korte intro geven. En in de loop van de inleiding zullen dus ook de sprekers en het studiebureau worden voorgesteld.
Dank je, Veerle. Beste mensen, ook van harte welkom vanwege mezelf. Ik ben Helga Verket, geoloog bij VPO. En ik geef een woordje uitleg bij het waarom van deze tweede studie rond dus dynamische modellering van reservoirs en efficiënt omgaan met ondergrondse ruimte. Het is namelijk een belangrijke Vlaamse beleidsuitdaging om te zoeken naar een efficiënt en planmatig gebruik van de Vlaamse ondergrond. Volgende graag. Mocht de volgende slide doen. Ik zal proberen zelf over te nemen anders. En dan kan ik hem zelf door scrollen. Maar bij mij blijft hij hangen. Ik weet niet hoe dat het voor de anderen is. Anders moet ze neem de besturing maar terug. Ja. En probeer nog eens naar de volgende slide te gaan. Ja. Want de uitdagingen voor de Vlaamse ondergrond vandaag die zijn groot. We hebben nood aan groene energie die jaar rond beschikbaar is. We hebben nood aan grootschalige energiebuffers die de variabiliteit van andere hernieuwbare bronnen kunnen opvangen. We moeten maatregelen nemen voor emissies te beperken. We willen voldoende en zuiver grondwater. We willen kritieke grondstoffen. En, dan mocht je naar de volgende slide, onze ondergrond, ja, die kan daar een cruciale rol in spelen. Bij mij blijft hij weer hangen. Ja, hij komt. Maar natuurlijk, dan moet uw lokale ondergrond ook geschikt zijn, de goede eigenschappen hebben. En ja, je kunt ook maar éénzelfde volume tegelijkertijd aan één toepassing toekennen. En dus, ja, als je kijkt naar waar zijn de eigenschappen van reservoirs het beste, dan zie je dat je al snel naar hetzelfde stukje ondergrond aan het kijken bent met meerdere toepassingen en dat je drukte en competitie ondergronds kunt krijgen. En dus, ja, moeten we proberen slim te gaan plannen. En dan mocht je de volgende slide. En dat betekent ja, dat je niet alleen efficiënt moet gaan afbakenen bij het toekennen van een vergunning, maar dat je ook eigenlijk optimaal moet gaan stapelen. Hoe zet je die vergunningen ten opzichte van elkaar, zodat je die efficiëntie daarin brengt en dat je probeert tegen te gaan dat je de ondergrond, die kansen die er liggen, suboptimaal gaat versnipperen. Daar moet je niet alleen je toepassingen goed voor kennen, dan moet je ook zeker je ondergrond zeer goed voor kennen. En dan kun je in principe slim plannen. Dan mocht je de volgende slide nemen. Ja, dat klinkt eenvoudig, maar dat is het zeker niet. En ons decreet diepe ondergrond legt vandaag al op dat aanvragers hun volumegebied zo gaan afbakenen dat dat enerzijds ja, groot genoeg is, zodat de relevante impact binnen die contouren valt, maar anderzijds ook klein genoeg, zodat er niet onnodig ruimte bezet wordt die dan niet meer zou gevaloriseerd kunnen worden voor andere toepassingen. En dus aanvragers moeten die evenwichtsoefening maken en daarbij expliciet rekening houden met alle toepassingen die er al zijn in een straal van 10 kilometer. En dat moeten ze doen aan de hand van een dynamische modellering. En zowel de potentiële interferentie als het planmatig beheer van de diepe ondergrond worden expliciet geëvalueerd bij het toekennen van vergunningen. En ook als nu na jaren opereren pas duidelijk zou worden dat je een invloed hebt die buiten die contouren die afgebakend zijn gaat, Dan nog zijn er regels in het decreet die gaan aansturen op een verplichte samenwerking of een aantal zaken aanpassen om dat toch terug te gaan optimaliseren. Dat zijn de basisregels. Maar het blijkt dat eigenlijk niet zo evident is, omdat we een heterogene ondergrond hebben, die soms moeilijk op voorhand te voorspellen is. En dus bij het uitschrijven van deze studie heeft VPO een aantal onderzoeksvragen geformuleerd. Ten eerste, hoe vind je nu dat delicate evenwicht voor een individueel project? Maar ook, ten tweede, ja, hoe doe je dat als je verschillende van die doubletten naast elkaar begint te krijgen? Hoe zorg je daar dan voor efficiëntie? Dat je niet alleen voor het project zelf gaat optimaliseren, maar ook eigenlijk je field development strategie erin krijgen. Ten derde hebben we ook gevraagd, wilt je ook naar tijdsaspect kijken? Want we willen niet alleen efficiëntie voor de mensen van nu, maar ook de toekomstige generaties. En als we de ondergrond gaan afkoelen, wat betekent dat allemaal, die doorkijk? En tot slot hebben we ook gevraagd, wilt je ons iets terugkoppelen over monitoring? Het is niet zo evident om in de diepe ondergrond te gaan opvolgen hoe dat allemaal zit met die interferentie. Je kunt dat voor een individueel project doen. Maar hoe kunnen wij daar kort op de bal spelen, zodat we dat ook goed kunnen managen? Dat zijn geen gemakkelijke vragen, dat beseften we. Dat was een uitdagende studie. VPO heeft die voor ons uitgevoerd. En ik geef graag het woord aan Madsen en Elger. Die gaan de resultaten toelichten.
Okay, good morning, everyone. Thank you, Helga, for the introduction already, providing the context and the research questions leading to this assignment, which is on dynamic reservoir modeling, with the aim to more efficiently define license boundaries in the deep subsurface of Flanders. This is obviously a teamwork, so not just me, I will be presenting the first part today. But we have my colleagues Edgar Hernandez, Justin Pogachnik, and Bernd Romat who also contributed to this study. And Edgar will be presenting the results of the modeling itself, and I will take over again towards the end, the conclusions and recommendations. This might be a bit of a repetition of what Helga just said, but it's nice to show some things on the map here. Where you see the red locations, the red areas are the current geothermal exploration licenses. There are 5, you can see maybe only 4, but there's one more, very small one in Bredene on the coast. And you see that 3 of them are within the Campine Basin. And you also see the vicinity of the gas storage, the subsurface gas storage site in Loonhout operated by Fluxys. In the yellow-orange color is the exploitation license, and the exploration license is indicated by the dashed area. And what is striking here is that both the gas storage as well as the 3 geothermal exploration licenses in the Campine Basin, they are located in a small area, but they're all targeting the same reservoir, the Carboniferous limestone group. So here the question arises: if you have multiple projects in a small area targeting the same reservoir, how can we ensure that we have a safe execution of activities? How can we ensure that the extraction of and use of heat is done in an efficient way and also in a sustainable way? And how does this fit in a broader view on the use of the deep subsurface? And these are criteria that the authorities and that VPO can use when looking at license applications in the future. We'll be looking here at the deep geothermal projects, more specifically the doublet, so systems consisting of a production and an injection well, not the single doublet systems, which are also coming into play recently. Now, the objectives is to use these to gain insight into a more efficient delineation of 3D volumes, because licenses are not just areas, they are actually 3D volumes defined in the subsurface. We do this for typical applications in Flanders, in our case for deep geothermal projects. And we wanted to simulate various concepts and scenarios by using dynamic reservoir models, try to gain insights for the typical applications, and based on that, make recommendations on how to more efficiently delineate or define these volumes, and what that means for evaluation or approval of licenses. This is a bit the methodology that we set up for the assignment. The main workflow, the main modeling workflow is what you can see on the right-hand side, where we started with establishing the structural framework and try to define typical reservoir settings or typical reservoir concepts. We have to define, of course, the scenarios that we want to simulate, and we have to look into the different variables that are relevant in this study, and we have to quantify these parameters before we can set up static and then subsequently dynamic reservoir models. We started the first part of the modeling by looking at sensitivity analysis. So looking at models of a single doublet and trying to see what the impact is if you would change a single parameter to an extreme value compared to having a base case, average case for all of the parameters. In the next step, we selected a number of these parameters as the most relevant, the ones having the biggest impact, and looked at models of single doublet systems, but combining all the parameter values, so both average values as well as extreme values on the high side or on the low side, and see what that means in terms of pressure and temperature impact around the doublets. For one of the reservoir concepts, we took it one step further by looking at field scale simulations with multiple doublets and trying to evaluate how the spacing of these doublets impacts pressure and temperature, and how that can impact heat extraction, both on a project scale and on a field scale. Before going to conclusion and recommendations, there are two other things that we kept in mind. One is that it's not just interesting to see what is the legal framework in Flanders and what is how are things currently done. It's also interesting to see whether similar situations occur in abroad, in regions or countries around us. Do we also have situations with multiple projects in a small area where we might have potential interference, and how is that handled in other regions? And then another part of the task was, as Helga mentioned, on monitoring. What can we do to reveal additional reservoir information, and how can we then use that? How is that relevant for project management? Now, going back to the map, this is zoomed in on the Campine Basin because this is where we are looking at doublet systems in the Carboniferous Limestone group, and there are currently 3 exploration licenses for that, and 2 doublets or 2 projects have been developed in Mol and Beerse. And you can see that against the background of a map showing the top of the reservoir according to the latest update. And in the past, these licenses were defined based on dynamic modeling, as it is mentioned also in the degree diepe ondergrond, where either you want to look at impact on pressure and temperature around the wells, and you want to define the licenses in such a way that they are large enough to encompass all the impact in the subsurface, but you do not want them to be too large, because that means you would be claiming areas and volume of the subsurface which is not really required and which would then remain unused, and that means it's not very efficient for an efficient use of the deep subsurface in Flanders. Now, first I will go to how things are defined abroad. So I mentioned, do we have already situations with multiple projects targeting the same reservoirs and present in a small area? And we do find that in three areas not too far away from us. One is in the Netherlands, in the Westland, so the area roughly between The Hague, Rotterdam, and Delft. And you'll see on the map here all the license areas that have been approved in different stages. So exploration license, starting license, follow-up license. And at the top right, you can see in a zoom in of the Rotterdam, The Hague area, where you also see in the red dots all the projects that have been developed. So there's quite a lot. I think I counted 14 in a very small area. So this situation of potential interference and having to look at how to define the licenses is something that has occurred there already. We find a quite similar or comparable situation in the Paris Basin in France, and we also have that situation in Germany in the area close to Munich, and that will be my next slide. Now, in the Netherlands, TNO did some studies and modeling on how to define these licenses, and what they do is use what they call the French method, and it's a method to define the license boundaries in a geometrical way, based on the well spacing, so the distance between injection and production well. And you can see this at the in the image lower right. Let me take the pointer here, where you have a production well and injection well. You can draw a circle around each of these wells with the radius equal to half the well spacing. And then the license boundary would be the rectangle, basically the envelope around these two circles. The argumentation behind that is that by the time the cold water plume, so the cold water front, propagating outwards from the injection well, by the time that reaches the license boundary, that would be about roughly the time that it would reach the production well, meaning you have thermal breakthrough, and that was considered as the end of the project lifetime. So reaching the license boundary is more or less equivalent in time to the project lifetime. It's not, TNO concluded it was not really a perfect method, but it's good enough to have a first approximation in homogeneous reservoirs. That's a very important remark to make. It doesn't hold in heterogeneous reservoirs, but for the homogeneous reservoirs they were encountering, this is a very good first approximation. And it's also quite handy in license applications, quite efficient to handle, because you don't need to go into the details of all the geology and the reservoir modeling behind it. It's a purely geometrical way that's easy to evaluate and to look at. So in France, we have a very comparable way of defining the licenses. In Germany, the situation is different. So licensing is defined at state level, but at federal level, sorry, but at state level, for example, in Bavaria, there are guidelines for applying for exploration and production licenses. So we have the two same licenses as we have in Flanders. For the exploration license, the extent of the license or the license boundary is based on the spatial scope of the work program that is proposed. So what exploration will be included in that work program. But for the production permit, the license boundaries have to be based on dynamic reservoir simulations. So that's, again, comparable to the situation in Flanders. What is different is that in Bavaria, certain values are explicitly mentioned in these guidelines, such as the maximum allowable drawdown of 1 bar or a maximum temperature change of 1 degree Celsius, which is not something that is not explicitly mentioned in Flanders, although it was used for the current license applications. And it's something that is kept in mind, but it's not explicitly defined. Now, towards our modeling workflow, we started with establishing the structural framework, which we have taken from the regional mapping that is present on the DOV, on the database for Flanders. And this is, again, on the top right, the most recent update for the top of the Carboniferous limestone group. And we defined several settings with typical reservoir concepts. And the first one we defined in the northwestern part of the basin, where the top of the reservoir is present below 1,000 meter depth, between 1,000 and 2,000 meters, under a rather thin upper Carboniferous cover. And you'll see here on the bottom right image a sketch showing the reservoir formation in light blue, cross-cut by a series of faults. And we envisage in this concept to have reservoir permeability along these faults. And we also have permeability in permeable layers, horizontal layers, where permeability is highest close to the faults and is decreasing gradually away from the fault. So you see the darker gray colors closer to the fault, getting lighter away from the fault in the middle of the fault block, trying to show the decreasing or declining permeability in this concept. We defined a second concept very similar to the first one along the southern rim of the basin. As you can see on the map, here the top of the reservoir is present below or shallower than 1,000 meters, and in places is covered directly by Cretaceous strata. What is different in the concept compared to concept 1 is that here we also envisage a karstified or permeable zone at the top of the formation. So what you can see here, in addition to a permeable layer inside the reservoir formation. Again, we have permeability along the faults. For large parts of the basin, the eastern and northeastern part, we see this as concept 3, where the reservoir is present deeper than 2,000 meters, increasing to 4 or 5 kilometers towards the Ruhr Valley Graben, where we don't have, and you can see that it has not been mapped in the recent update, where we don't have well data to confirm that. Here we don't expect extensive karst or permeable layers in the formation, but we expect permeability to be confined close to or inside the fault zones, and in some layers, but rather closely to the fault zone. So permeability will be decreasing quite quickly away from the fault zones. Now, this is how we translated this in the concepts into the reservoir model in 3D. You'll see first a cross-section view. We have a top view or a map view here, and then a 3D view on the right. And here you see in colors the reservoir layer offset by a series of faults. And the faults create a series of horst and graben structures. And you see the red colors indicating higher permeability values, and then the color gradually changing to blue, indicating the declining permeability values as we move away from the faults. You see the same in the map view, with the red colors indicating the presence of the faults and the layers closer to the faults. And we also have a set of perpendicular faults, a secondary set of faults, which we have taken into account in the modeling. Now, these basically define a series of geometrical parameters. One is the karst extension, or the extension of the permeable layers away from the faults. We have the fault spacing, the height, and the throw. And we also have the layer thickness that we are looking at. There are also, of course, other relevant parameters in the dynamic reservoir modeling. The series of petrophysical parameters, so the porosity and permeability of the matrix, the reservoir layer, and of the faults themselves, and also the thermal properties of the rocks. And we selected a number of these parameters for each of the concepts, and most of them are the same in each of the concepts. There are some small differences. For example, for concept 2, because of the additional layer at the top, the separation between the top and the bottom layer is an additional parameter to be looked at, and also the permeability of this top layer. Another important thing to variable in the reservoir modeling are the well configurations, and I'll show that for concept 1. We have a top view or a map view here at the top, and some 3D views here at the bottom, where we defined three well configurations, one which we have chosen as the base case, and then 2 others which we are looking at as the extreme cases, let's say. The base case has a production well located inside one of the wells. The idea behind that is that we want to maximize permeability, so highest permeability is found closest to the wells, and we also want to tap in the deeper reservoir layers and the deeper fault zones where higher temperature can be produced, deeper layers inside the graben. So this is the positioning of the production well. The injection well is here situated on the horst. The advantage of that is that it is shallower, so you optimize in terms of cost. We have not positioned it in the middle of the horst because this is where we, according to the concept, will find the lowest permeability, but it's slightly offset from the middle. So also not in the fault zone, because then we would be injecting directly in the fault zone, increasing pressure, and safety-wise, that's not a choice to be made. These are the 2 alternatives that we have chosen. One has the production well in the middle of the graben, so targeting the deepest and hottest reservoir zones. It keeps the injection well in the same position in the horst. And then our final case has the production well again in the fault zone, but in injection well inside the horst. Okay. I think, Edgar, I can give the word to you.
Can you help me with the slides? Okay.
Yes.
Good morning. Thank you, Madsen, for the introduction of the reservoir concept. And that's, as mentioned already by Madsen, we will go through the simulation study that has as an objective to understand the size of the disturbed thermal area and the disturbed pressure area in the different reservoir concepts. This parameter is important because we want the licensed production area to cover at least the disturbed temperature area. It's important to mention that the disturbed temperature area is an area defined by a contour of 1 Celsius degree in this study of temperature change after geothermal operations, after the operation reached the cold water breakthrough. I mean that the production temperature in the producer well reduces 2.5 degrees in this study. We will then discuss the sensitivity analysis. Then we will speak a bit about also the recharge of this reservoir after stopping operations, how long it takes for recharging. Then we will discuss the permutation analysis between those parameters that are relevant. And then we will discuss more about the interaction of multiple geothermal doublets. So let's start with the sensitivity analysis. The idea here was to define which parameters of the reservoir, I mean geometrical or petrophysical parameter, are relevant to consider during the definition of the license area. And we did this for the different reservoir concepts. But before going to the results, only want to mention the condition of these cases. We use only a single well configuration for this case, enclosed in an area of 5 by 6 kilometers with a maximum production rate of 200 cubic meters. But if the reservoir property doesn't allow to inject this flow rate because pressure is too high in the well, the flow rate is decreased. So here in the figures to your right, you will see in the middle a bar indicated and the average disturbed thermal area for the base case in the concept reservoir number 1, which is a value of 4.5 square kilometers. And then we can see in this tornado plot how the different tested parameter affects the disturbed thermal area. And it's then easy to note that the karst tension from the faults, I mean the permeability in between the wells and the well configurations are the ones that really impact the size of the disturbed temperature area. So if permeability in between the well is high, then the disturbed temperature area is small. But in the other way around, if the permeability in between the well is small, the disturbed thermal area is quite high. For the case of the well configurations, if the wells are in the same structure, let's say in the graben, the disturbed thermal area is the smaller one. We can also see in the figures that the shapes of the disturbed thermal area here colored in blue. After exploitation, they have a triangular shape and usually elongated along the faults or parallel to the faults due to the reservoir heterogeneities that are considered in this concept. This gets more important in the figure at the bottom, where the disturbed temperature area extends kilometers along the fault because the permeability in between the well in this concept is not that high. So we go to the next slide. So now we show also the result for concept number 1 in terms of pressure. Pressure area is pretty sensitive, again, to the karst extension from the fault, but also to the maximum porosity permeability of these karsts. So pressure will be a function of pressure, disturbed pressure area will be a function of the permeability. So that is the important parameter. If permeability is high, the disturbed temperature pressure area will be small. Otherwise, if the permeability is really small, the disturbed pressure area will be high. Yeah. In addition, other parameters like permeability and isotropy. I mean, the ratio between the permeability in the direction of the north or the y direction and the permeability in the s direction is low. This will also affect the size of the pressure, disturbed pressure area. So next, the same results were obtained for the two other concepts. Concept 2 were mentioned by Madsen. It also contains an upper layer with continuous and homogeneous permeability. And also the same results were obtained for concept 3. Again, disturbed thermal area in concept 2 has already for the base case a smaller size than concept 1 because of this continuous layer. So the area in this concept 2 for the base case is about 3.3 square kilometers. And it can range from 1 square kilometer to 6 square kilometers. For concept 3, what really matters, because concept 3, basically the flow is parallel or along the faults. Then what really matters is the permeability of the faults between the wells, between the injector and producer well. If permeability of this fault is high, the disturbed thermal area is small. So, but all the way around, if the permeability of these faults that are in between the wells is really low, then the disturbed thermal area is high because the water doesn't go directly towards the producer well, the cold water, but it is spread along the faults. Okay, but then before getting into the recharge time, then what is important from the sensitivity analysis or to stress is that permeability of the faults, of the cards, or the anisotropy of the permeability are the most important parameters when trying to understand the size of the disturbed pressure area and disturbed thermal area that then should be considered when defining the license production area. That's it. Okay, then in top of the spatial definition of the license area, we also explore the influence of time in this license area and how fast the system could get recharged. For this case, we consider the base case of concept 1. And we use an injection flow rate of 200 cubic meter an hour and an injection temperature of 30 Celsius. This model considers only heat conduction as the mechanism of recharge. It's important to note that other mechanisms like convection could also exist in the system, especially if high permeability deep faults are in the system. But we started, or we did this study with, let's say, the more conservative case, that is only conduction. Okay, then I would like to stop a little bit here in the figure. So in the figure in the top left, we have the recharge time for different exploitation times. I mean, you exploit 20 years, 30 years, 40 years, or 80 years with the given conditions. Then at time 0, you have used, you have left certain amount of heat, for instance, 90% for 20 years. And then we can see that to recovering back the heat that has been extracted, you need, depending on the production time, between 1,000 and 2,000 years if you want to recover everything for this model. In case you want to recover only 90 to 95%, then a much more shorter time is required, between 100 to 200 years, depending on the conditions. Yes, we want to stress that this result might look a little bit pessimistic, but are based on only conduction. The basin is still underexplored. That's something that we also saw as experience in the Paris Basin, that at the beginning, the forecast of the duration of the project was 30 years maximum, but after more and more projects have been executed and more data has been acquired, it had been seen that the performance of the project can be better, they can last longer, and they could recharge faster. Next. So now we go to the permutation analysis. Here, as mentioned by Madsen previously, we took the parameters for the concept 1 that has a major impact on the disturbed pressure area and disturbed thermal area. And we want to know how far does the thermal impact reach if stream parameter values are combined. So we run multiple permutations and we end up with these frequency plots for thermal area at the top, where we can see that the thermal area can go from very, very low values to almost 4 square kilometers. And that depends again on the properties of the system, where especially the permeability again of the cards. If the permeability of the card system is small or the card extension is small, then the temperature area for these cases are the smaller because you inject the lower amount of water because of the restriction for injection. Other way around, the distribution have more or less, for the other cases, an average of 2.5 square kilometers. Then also here in the figure at the bottom, we can see that the shape of the thermal area defined by these contours is again a triangular shape. Is basically defined by the heterogeneity of permeability between the injector and the producer well. Next. For concept 1, in terms of pressure, again, what we can see here is a very wide extension of the disturbed pressure area that can go to almost a zero thermal area. When the system is really permeable, then the values of the disturbed thermal pressure area are very small. But all the way around, if the permeability of the system is small or the permeability of the faults that are indicated in the figure below with the black lines between the wells is also small, then the pressure area can be really high. So again, here the message is trying to avoid placing wells between faults that might be almost sealing or with low permeability. So it's an important message when designing the well location. it's important to guarantee that there is a hydraulic communication between the wells. Otherwise, disturbed pressure area can get important, and this also can affect the maximum injection and production flow rates from the projects. For concept 2, the system shows for the thermal area a bimodal shape that is basically ruled by the heterogeneity or the anisotropy of the permeability. If the anisotropy is low, close to 0, then flow rates tend to be lower, and then the thermal area is low, here indicated in red. While when the anisotropy is equal to 1, then the shape of the thermal area starts to be more rounded, as indicated in the figure at the top right, and then gets more similar to the shape that was shown by Madsen in the French method. In terms of pressure, again, is very variable, can go from very small to very high depending on the permeability of the layers and the folds. Next. That's Madsen. Okay. Next one.
You want to move to concept 3?
Yes. Yeah. Concept 3 is the concept where major permeability is along or parallel to the folds. And in this concept, thermal area, again, has more or less similar values, but distribution is different than the other concepts. Especially the thermal area goes closer to lower values of 1 to 2 square kilometers. And this is due to really high permeability of the folds, or also to really low permeability of the folds. When you have low permeability of the folds, then the injection flow rate is really small, and then the affected area is also then really small. Again, here the shape of the system is really elongated along the folds that are close to the injector well, as shown in that figure. So, as a conclusion from the permutation study, depending on the characteristic, again, of your reservoir, the shape of the area can be very different, and we need to focus when doing the forecast in the permeability of the layers and the permeability of the folds in order to forecast the disturbed pressure and thermal area, and then try to define the production license. Next. Multiple doublet. We started interfering between projects by simulating a field of 9 doublets. And these 9 doublets can be ordered in a line drive pattern where the wells are aligned along the folds, or an offline drive pattern where we leave a space in between the well doublets. And we wanted to understand what is the impact and what could be the recommended strategy for improving the performance of the individual doublet, but also the performance of the whole field. For this case, we use also the concept 1 and the well configuration named as L shape. So next. So for the line drive pattern, here in the graph to the right, top right, we plotted the doublet spacing versus the aerial sweep efficiency. The aerial sweep efficiency is the area contacted by the cold water in these 9 doublets, and versus the heat production in green and the COP in red. And what we can see is that if we put the projects together, we improve the aerial sweep efficiency, the blue line, as you squeeze the project, so you contact more area. But in the performance of the individual projects start to decrease, start to produce lower energy and lower COP. We did the same for the off-drive pattern. If you can go to the next slide. And for this system, if we check the same plot to the right, we can see that the aerial sweep efficiency again increases as we put the project more together. But in this case, the decrease in gross production only start to be important when the spacing between the projects is more than 4,000 meters. So this system is a little bit less sensitive to interference between projects, especially because there is let's say there is a space in between projects, and because projects can help one to each other. One injector can displace water not only to the producer of a given doublet, but can also displace some water to the neighbors. So improving sweep efficiency, but also improving hydraulic communication. So then, after the simulation results, then we wanted to know how could we monitor these projects in order to understand and support future reservoir simulation studies on forecasting the pressure distribution and the temperature distribution of these geothermal fields. And then, of course, what is important to measure also to avoid geological risk is pressure. But the only problematic with pressure is that we need wells for doing so. So the strategies could be using observer wells dedicated for monitoring. This well can be made on purpose for this kind of objective, or can be wells abandoned from previous geothermal projects. And pressure can be also monitored doing cyclic pressure buildup and fall-off. But these are punctual information, and we need to use this information together with a large geological and dynamic model to understand or to forecast what is happening in the whole system. Temperature is a second variable also important to monitor. Again, observer wells could be the way to monitor directly temperature behavior and understand how the disturbed temperature area is advancing in all these projects. But we could also have indirect techniques like resistivity survey techniques that, after proving that they can be deployed in this kind of system, could help to define how the temperature distribution looks like at a certain time, and then make actions on managing the doublet field. This one. There are also additional variables that we could monitor. For instance, fluid flow directions. This could tell us about the flow pathways and the interference between license. But this can be done via injection of tracers and sampling in production and observable wells. This is a direct indicator of flow paths. There's no need of stopping operations. But the challenge is having sufficient different traces as running projects, because we want to identify from which project is coming the water. So we need probably a different tracer for every project. And then the last recommendation is about rod deformation. So it's recommended to monitor seismic activity or subsidence or uplifting. And this can be done via seismic monitoring networks or satellite radar interferometry for the uplifting and subsidence of that could be caused if extreme depletion or extreme pressurization is causing the system, even though it's not expected. And with this, I think I finish my slides.
Okay, thanks, Edgar. Maybe a few words on conclusions and recommendations, where we wanted to focus on how to define the licenses. And we, in the first part, I talked a little about this French method, the rectangle around the wells, which is a pretty good approximation in homogeneous reservoirs. But however, as you can see on the graphs on the right-hand side, we have temperature impact here at the top for the three concepts. We have pressure impact at the bottom. You see that the rectangular area based on the well spacing will not be very adequate to define the licenses and to encompass the impact in the subsurface. And there's a slightly better fit in concept 2, because in concept 2 we have a homogeneous top permeable layer, and that brings us a bit closer to the assumption of a homogeneous system. So in terms of the license definition, it would be more efficient to use something adapted. It can start from the geometrical approach, where, for example, you look at a conservative estimate of the thermal impact area. Here we looked at about 75 or 80%, P80, let's say, of that size, which would result in this contour for the temperature impact and a rectangle around that. Obviously, this would be too small because there will be some pressure impact around the two wells, and here around the production well, that pressure impact will be outside of the license boundary. So we propose to increase the size of the license so that at least it has twice the well spacing. So between the wells and the boundary, you would have at least half the well spacing to account for the pressure impact around the wells in themselves. So here we focus on the thermal impact, because in the end, that's the most important one to look at. If you look at interference between projects, we have considered interference of 1 or a few bar in terms of pressure to be not so relevant, but the temperature impact and cold water breakthrough would be more relevant in sizing the licenses and spacing the licenses. Spacing is something that we looked at from the multiple doublet, the field simulation, where we had spacing around 4,000 meters, which is where the field efficiency would still go up at shorter distances, but individual projects would suffer from a shorter distance negative interference from that. We've tried to put also this on a map to illustrate it for concept 1. And then we came up following the proposed procedure, looking at the results of the simulations and also the model assumptions, and looking at the spacing between the doublets as recommended from the multi-doublet analysis. You could come to this kind of geometry of geothermal licenses in the concept one area, and then we are around 20 licenses. But you can also see that a number of those, I think here 7, are already positioned within the safety perimeter around the gas storage site. So further study there has to be done about that interference. But this gives us an idea about what is possible in this part of the basin, looking at these license sizes and also looking at spacing between the licenses so that we allow for a first generation of projects, but also a second generation of projects. And you could increase that by including less projects in the first generation. You will leave more open space for a second, a third, and a fourth generation before coming back to the original location at the end of the recharge time, and then use it again with minimal loss of heat in place. You also see or notice that the current licenses are bigger, and certainly the one around Mol, which were granted conservatively large, trying to take into account the initial uncertainties in the basin, and also taking into account, of course, the work program that was proposed at the time, which is different from the 2 licenses that we have in Beers and Turnhout. So eventually licenses will become smaller than what was granted here initially. I think that's my last slide. We have one more slide here showing or pointing to the results, which will be made available at the FRIS portal, where we will have both the report, but also a brochure that was made, and also the data sets behind the modeling. So the input and the output files will all be present there. And the report explains which files, which folders contain what type of results. But I think now it's time for questions. Helga.
Yeah, thank you, Madsen and Elgar, for explaining. I haven't seen questions in the chat, so feel free to speak up if you have a question. Je mag ook vragen in het Nederlands stellen. Beide talen zijn oké voor de discussie. I think it needs time to sink in and reflect.
There's quite a lot of results and graphs, so it indeed it's a lot on your plate, and it might need time a bit to sink in. But I think therefore the brochure also will be a nice short recap or synthesis of the study, without digging into all the details that you can find in the report itself.
Yes, I would like to add that when thinking about defining the license area, we need to think that the system we are dealing with is really uncertain, even though we have some seismic lines or well data. We need to consider that there are different options, and these different options should be, let's say, modeled and try to define the license area so that most of the possible options of possibilities are covered by the license production area.
Yes, it was a challenging study and a huge amount of work, but I like the idea that we started from the reservoir concepts, because you don't know, but you have to start with the reality that we know so far. And then you added a very structured a strategy where you were really, to say, you tested like quasi everything, but in a structured way, so that you take the best of both worlds. You take these concepts and you take the structured work, and there is a lot of info in it. So for those that are interested in technical details, check these data. And there are a lot of lessons learned also for us, for the policy framework. We will use the insights not as a direct policy rule for tomorrow. I also think that people that are interested to request a permit will take their advantage in the work you did. And indeed, the brochure will probably be maybe the first step for most people, and then you see which detail you need further, and you can dig into the technical report. If there are no other questions, then I just want to thank all the team. Edgar, Justin, Bernd, Matze, good job. En thanks. Dank ook aan iedereen voor te luisteren. En als er later vragen opkomen, mag je altijd contact opnemen met ofwel mij ofwel Matze als coördinator van de studie.
Dan denk ik dat we hier kunnen afsluiten. Hè.